Good morning, good afternoon, good evening. This is video 10 of STAT 248, Couplings in Monte Carlo. In this final video for this course, we will look at one of the most exciting methods based on couplings of Markov chains, called coupling from the past. That's a method to obtain exact samples from the target distribution of interest. So previously, in this course, we looked at couplings of Markov chain Monte Carlo algorithms to analyze their convergence properties to obtain geometric ergodicity results. And more recently, we looked at couplings as an ingredient of methods of algorithms to obtain, for example, convergence diagnostics, and by which we meant upper bounds on the total variation distance between pi t, the marginal distribution of the chain at time t, and pi, the limiting distribution or stationary distribution. We're interested in obtaining upper bounds on this quantity in order to choose a choice of burn-in for MCMC estimates, for example. So we've seen different convergence diagnostics based on coupled chains. And we also looked at ways of using coupled lagged chains to obtain unbiased estimators of target expectations, meaning integrals of functions h with respect to the target distribution pi. So, for example, we looked at an estimator denoted by h little k equal to little h of xk plus an infinite sum of differences between h of xt and h of yt minus 1. And we've seen that this estimator is unbiased in the sense that under some conditions, for example, conditions on the meeting time having geometric tails, the expectation of the estimator is exactly the quantity of interest, and the variance of the estimator is finite. The expected cost, which is essentially the expected meeting time, is also finite under adequate assumptions. And so we could deliver unbiased estimators as opposed to the standard MCMC estimators. So today we go further in that direction and look at coupling from the past, often called CFTP, which is a method in the class of so-called perfect sampling or exact sampling algorithm, just like rejection samplers, for example. But coupling from the past employs, of course, couplings of algorithms, couplings of Markov chain algorithms, for example, using common random numbers, but in principle, any type of coupling to obtain exact draws from pi. So first, I'll discuss a little bit the difference between exact sampling, or perfect sampling, and unbiased estimation. The differences in terms of practical differences for a user. So first, if you can do exact sampling and obtain x from pi, then h of x will be an unbiased estimator of the quantity of interest, this integral of h with respect to pi. And so being able to do perfect sampling, in particular, allows unbiased estimation of integrals. Conversely, if we have unbiased estimators of integrals, for example, using lagged chains, even if we have unbiased estimators of an entire class of integrals for the functions h, for example, in a whole class of functions, it's not clear that we can obtain exact samples from pi. We don't know, in fact, whether there's a generic way of turning unbiased estimators into perfect draws. So in the absence of a known technique, we cannot be sure that there is such a technique, and so it doesn't seem at the moment feasible to obtain exact draws from unbiased estimators. And there's a practical difference. In particular, one very visible difference when you're employing perfect samples is that h of x is not only unbiased, but it's taking values in the range of the function that you're trying to integrate, almost surely. On the other hand, if you're employing an unbiased estimator, such as the one we described before, this capital HK estimator based on lagged chains, then the value of the estimator might not be in the range of the function h. So you might have estimates that do not take values that are sensible with respect to the quantity of interest. So for example, suppose that you have a function h that takes values in the interval 0, 1. For example, h is an indicator function, the indicator that some x is in a set A. So then the target expectation is the mass of the target pi for the set A, so it's pi of A, and that's a number between 0 and 1. However, the unbiased estimators above will not give values between 0 and 1. So why is that a problem? Well, if we had values in 0, 1, for example, if we had perfect draws, x1 to xn from pi, then via Höfding's inequality, we would obtain a concentration inequality on our estimate, which is given by the average of the function evaluations at x1 to xn. So concentration inequality goes as follows. The probability that the estimate differs from the expectation of interest by more than a quantity little l, for example, probability that this occurs is in fact less than 2 times an exponential in n and l square. And so we have very strong guarantees that the probability of doing a large error for our estimate decreases very quickly with the number of samples. But Höfding's inequality only holds here because h of x is in the interval 0, 1. It would hold also in a different version for any bounded functions. And so on the other hand, if we have our unbiased estimator hk, we have no guarantees that the estimates are in the interval 0, 1. So in order to construct confidence intervals, we can employ a central limit theorem. Perhaps we can employ some approximation of Chebyshev's inequality based on an estimate of the variance. But we cannot apply Höfding at all because our estimates are not bounded. And so we are losing something very concretely here in terms of our guarantees, the guarantees associated with our estimate. So in a very concrete way, perfect sampling really is better than unbiased estimation if we don't have further guarantees on our estimates. So if we don't have, for example, guarantees on the range of values that the estimate can take. So now that we are motivated to obtain perfect samples, let's have a look at how to do it from the perspective in the setting of a finite state space. So assume the state space is made of n elements, 1, 2 to n. It's a finite state space, and we imagine a Markov chain on that state space, taking values in that set. We're going to denote this Markov chain by xt, like always. And it has a transition capital K, which here corresponds to an n by n matrix with each row summing to 1. We assume the invariant distribution of this chain is the target distribution pi of interest. And to understand coupling from the past, we will make use of this iterated random function representation of the chain. So we can write xt as a function psi of the previous state xt minus 1 and some random input ut. So psi here is a deterministic function of 2 arguments, the previous state, which is in 1 to n, and ut, which is a random input. For example, we can assume that it's a uniform in 0, 1, and we can assume that the UTs are independent of one another across times. Alternatively, we can write xt as psi t of xt minus 1, where here psi t is a random function. And it's denoted with a slightly different psi here to refer to the fact that it's a different object, it's a random function. And what it might be, for example, is exactly the little psi above for a given u. So big psi t dot would be little psi dot comma ut, where ut again is a random variable. So the function big psi t is itself a random function. So let's take an example with, for example, n is equal to 4. So there's only 4 states in the space. It's a very simple setting. In that case, the transition is given by a matrix, 4 by 4 matrix. So for example, we can fill up the matrix with entries. As long as the rows sum to 1, it will be a valid transition matrix. And we will be careful also to make a transition matrix irreducible, which means that all states can be accessed, maybe not from all states at every time, but overall the Markov chain should be able to go everywhere. So here's an example of a matrix with just 1/2, 1/3, 1/6 as entries and zeros. So here Kij at the row I and column j refers to the probability that xt would be equal to j, given that xt minus 1 was equal to I. So it's the transition from I to j over one step. So associated with this transition matrix, we can imagine random function psi t. And so we can represent it using arrows going from the 4 states to the state space itself, so from big X to big X, where, for example, from state 1, we might go to state 2. From state 2, we might go to state 1. From state 3, we might go to state 4, for example. That's possible based on the matrix K. And from state 4, we might go to state 2, for example. So those arrows correspond to a plausible realization of this random map. And we can write that for a certain ut here, psi of 1 comma ut is equal to 2, psi 2 comma ut is equal to 1, and so on. So those arrows are very convenient when describing coupling from the past and will be used repeatedly in the coming slides. Note also that this can be implemented on the computer, and you could store this set of arrows simply as a vector of n elements, where each element encodes an image of the element through psi. So this set of arrows can be simply represented by a vector of size n with entries in 1 to n. So next we'll look at an idea that might seem like it works, but it doesn't work. And it's important to understand why it doesn't work to appreciate the method that does work, coupling from the past. So the first ID would be a forward coalescence ID. So simply, it means employing those arrows as represented before, going forward in time. And so we would go from time 0 to time 1 as before. So let's draw a set of arrows from the states 1, 2, 3, 4 to the states 1, 2, 3, 4. There we go. We can see that the chain would transition if they were in those different states according to the arrows. And then we can continue adding arrows to the right, going from time 1 to time 2. For example, with this set of arrows. And then we can continue to go from time 2 to time 3. So let's represent the arrows going from time 2 to time 3 and simply represent those ones which could be reached from time 0. So you can see here what happens is that when we go forward, eventually all the paths described by the arrows would coalesce to a single state. So at this point, for example, with those arrows, you would end up in state 1 at time 3 for any x at time 0. So that means that when we compose the random functions psi3 of psi2 and psi1 starting from any little x in 1, 2, 3, 4, which we can write also with circles, we obtain 1 for all x. And so at that point, it's clear that the value of x has no influence on the obtained value at time 3. And so here it's very easy, very tempting to say that since the initial state has no influence anymore on the coalesced state at time 3, it would be easy to say that this obtained state would be a draw from the stationary distribution pi. Right? So that would be a reasonable claim that when we compose from time 1, 0 to 3 from any x and we get the same result, we obtain a draw from pi. We can write the coalescence time, forward coalescence time, capital T, as the first time, little t, at which the cardinal of the image of the whole state through the composition of functions up to time t is equal to 1. And so the cardinal of the image equal to 1 means all the arrows have coalesced into one state. So these vertical bars here denote the cardinal of a set. And that set is the state obtained when propagating all of the initial states through the composition psi t of psi t minus 1 all the way up to psi 1 of x. So that's our forward coalescence time. So there's a question, of course, regarding whether it is finite. But the answer to the question above first is that no, even though the coalescence time might be finite, the state at the coalescence time is not a draw from pi. And it's easiest to see this via a counterexample. So in particular with the matrix K described before, there was a state among 1 to n that could only be reached from one of the other states. That was state 4 in the example before. It could only be reached from state 3. And if you have such a case, such a state that can be reached only via another state, then it's easy to see that this state K cannot be obtained as the forward coalescence state. It will never be the place where the chains would meet for the first time. Chains would have to all be in the state J before in order to be in the state K after. And so the coalescence would have occurred before. And so that means K can never be the output of this forward coalescence procedure, even though K could very well be non-negligible with respect to the target pi, of course. So that should be enough to convince yourself that this forward coalescence procedure does not produce draws from pi. And another thing to note is that even if we started the chain at stationarity, it is not the case that x capital T is at stationarity for all random times t. In particular, the random time can be a stopping time that depends on the path, and so it can bias the distribution of x. Whereas, of course, if we look at fixed deterministic times, then if x0 is stationary, all the subsequent times would be stationary. So the key idea in coupling from the past, the really beautiful idea and very novel idea of this innovation from the 90s is to look at the backward coalescence. So what does it mean? We start again from time 0, and we write the 4 states, but we're going to iterate backward in time, meaning we're going to see how we can arrive at time 0. So for example, we could have been following those arrows from time -1 to 0. Previously, we could have followed those arrows from time -2 to -1. And again, previously, we could have been started from any of those states at time -3 and followed those forward arrows going to -2. And at this point, you will observe a similar coalescence phenomenon that we observed previously, but going up to time 0. So let's trace all the paths following the arrows from time -3, just following the arrows from those 4 starting positions. And we can see that we arrive always at state number 2 at time 0. So we have a coalescence phenomenon just like the forward coalescence. And indeed, it doesn't look much different at this point, but you will see that the procedure is much different because it provides perfect samples. So we will define backward coalescence times, T star, as the infimum of t's larger than 1, such that when we compose the functions in the other direction, so now we're writing psi 0 of psi -1 of all the way to psi minus t of x, and we look at the cardinal of this image, and when this cardinal is 1, then we have coalescence. And this is what happens in the figure above. And so T star is the first time at which the composition from the past becomes effectively a constant function, meaning if we apply these compositions to any of the states at that time in the past, we arrive at the same state at time 0, so the function is a constant function. And now we can claim that the value of that function at time 0, which we can denote by yt star, which is the composition psi from time minus t star to 0 evaluated at any of the points, because by definition we would get the same value from any of the starting points. That variable follows pi. So you see the key difference is the order in which the functions are composed. And we've seen before in chapter 3 that the order of the function, the random function compositions, is quite important, results in trajectories that are significantly different. Even though it might look superficially like the order does not matter, since all the psi functions are IIT. So note first that T star might be finite, almost surely, or not. That depends really on the choice of the iterated random functions. So for the same Markov kernel, you could find random functions that would result in coalescence, and other random functions that are equally valid, but that would not result in any coalescence. There's a result saying that if the chain is irreducible, so if it can go from anywhere to anywhere in at least some steps, then there is a choice of function that would work, that would result in almost surely finite backward coalescence times. So now let's show that the result of this procedure indeed is a draw from the target distribution pi. So let's look at the distribution of this yt star, and note that we could have continued iterating the functions all the way to minus infinity, and we would have still resulted in the same state at step 0, same state number 2 here, simply because now we know that from any state at time -3 we arrive at state 2 at time 0. So it doesn't matter what would have happened before. So we can imagine a chain that would have been started at time minus infinity, and of course which would have converged by time minus 3. And so that chain, which is stationary, would arrive at step 0 at the state number 2, and that's our perfect state. And so note also that, again, by the IIDness, the independence and identically distributed function psi, the YT process with the composition backward is equal in distribution to the standard XT process where the functions are composed forward, which means the newest function psi t is applied to the previous result. There's an equality in distribution at all times t. And so if we assemble all of those arguments together, we find that the total variation distance between the law of YT star and pi, it's the limit when t goes to infinity of the law of YT minus pi in TV. That's because if we had started the compositions infinitely far in the past, we would have arrived at the same y as YT star. Now for all t, the law of YT is the law of xt, and so the limit of the total variation distance between the law of xt and pi is 0. So the algorithm produces draws from the target distribution pi. Let's summarize the algorithm in a pseudocode format for clarity, and just to emphasize that we can in fact implement this algorithm. So we start at time 0. We define psi 0 to be the identity map initially. So it maps each state to itself. And then repeatedly, we take a step towards the past. So t becomes t minus 1. We sample a new set of arrows. That is, we sample a random input ut, and we set psi minus t to be psi dot ut, u minus t, however you want to call it. The time indices are slightly confusing here because we're going to the past. So this new psi is a new set of arrows in the past, and we can compose the arrows up to the time 0. So we obtain the function compositions, psi 0 of psi minus 1 of all the way to psi minus t. And we compose until the arrows coalesce. In other words, until the composition is a constant function, or equivalently, until the cardinal of the image is equal to 1. And at that point, we exit the loop. We can output the time, t star, at which we exited the loop, and the value of the unique element in the image of the set by the composition. So the theorem that we've looked at before effectively says that if the output time is finite, so we have a well-defined output, then this output is distributed according to pi. This composition from minus t star to 0 applied to any x is distributed according to pi. So it's a perfect samples. And so this is the most basic coupling from the past algorithm. Of course, it's very discrete in its presentation here. So it requires storage of functions, this set of arrows from x to x. And so in this naive form, it would only apply to very small finite state spaces. So next we will look at one of the variation called monotone CFTP, which allows to apply coupling from the past to a restricted but still challenging set of examples. So this is one attempt at going beyond small finite state spaces called a monotone CFTP. And that's in the original paper by Propp and Wilson. They introduced both the original naive algorithm and the monotone version. So the assumption here is that there is a partial order on the state space. And according to this partial order, there are extremum denoted by 0 hat and 1 hat. Those are states in big X such that all states are between 0 hat and 1 hat. So it's a partial order, meaning that some of the states cannot be ordered with respect to one another, but we assume that they all are larger than 0 hat and smaller than 1 hat. So the canonical example for this is the Ising model, where the state space is a grid of size n by n, where there's a -1 or a +1 at each site. And so as a partial order, we can consider that x is less than y if at every single site xi is less than yi, where xi, yi are simply -1 +1. And of course, -1 is less than +1. So then 0 hat would be the grid with -1s everywhere, and 1 hat would be the grid with +1s everywhere. So we can think of 0 hat as the grid with minuses everywhere, and 1 hat is the grid with pluses everywhere. Instead of minuses and pluses, you can think of zeros and ones, or -1s and 1s, and +1s. So we assume this, and furthermore, we assume that the partial order is preserved by the propagation through the maps psi for a fixed u, fixed random input. So if x is less than y, then psi of xu is less than psi of yu, almost surely. So for almost all u. And this again applies in the case of the Ising model to the most naive implementation of the Gibbs sampler, also called the Glauber dynamics in that case. Either systematic scan or random scan Gibbs sampler. So if we are in this setting, under those assumptions, the key idea is that instead of keeping track of the coalescence from all states, it is enough to check simply that coalescence occurred from 0 hat and 1 hat. In other words, to check that the cardinality of the composed maps from time 0 to time -t is equal to 1, it's enough to check that starting from 0 hat, we arrive at the same place than if we start from 1 hat. Indeed, thanks to the ordering, we would then know that starting from any x would have also resulted in the same state. So we can think of the states 1 hat and 0 hat as above and below all of the states. And so if we have coalescence from -t, meaning the chains eventually reach the same state at time 0 if started from -t from either 0 hat or 1 hat, it means if we had started from any other places, we would have coalesced to the same location at time 0. And so that's the key development that helped Propp and Wilson in this 1996 germinal paper on the topic to tackle an Ising model with, in fact, a very large grid. So 4,200 square sites. So the cardinality of the state space would be way too big to enumerate completely. So we couldn't apply the previous implementation of CFTP, but we can apply monotone CFTP. There are further remarks to be done regarding implementation of monotone CFTP. So let's look at first a naive implementation of monotone CFTP. So we would start from time 0, and then we would repeatedly decrease time by one unit. So we go from time 0 to -1 to -2, etc. Every time we conceptually sample a new random input and compose it with the previous steps, so that means the future times random input, to obtain the composition psi minus t to 0 as the previous function. So using the inputs, the random inputs that we have obtained at the future times with the new psi minus t. Then we check if coalescence occurs from 0 hat and 1 hat, only from those two states, because this is enough under the assumptions on the partial order. And if we have this equality, we output the time, t star, and the value of this function composition evaluated from any x, so from 0 hat, for example. So what is the cost of this procedure? The cost is the cost of computing at every time t twice the composition, one for 0 hat and one for 1 hat, and checking that the results are equal. So typically this would cost order little t at step t, and so overall this would lead to a cost that is quadratic in t star, the coalescence time. And so there's a way of reducing this cost significantly called the doubling strategy, which consists in starting from, again, the initial time. So here the time is going to start from -1, not from 0, simply because then we will be able to double the time. So what we want to do is to go from 0 to -1, but then to -2, then -4, then -8, -16, and so on. So we do not consider every single time, but only powers of 2 with a negative sign. So then again, at every step, we conceptually imagine that we sample new random inputs and obtain associated functions, and we compose them with the function of the future time steps. Again, being very careful to compose them in the appropriate order to have a backward coalescence and not a forward coalescence. And so we compose the previously obtained function with the new random function. And then we check equality from the composition started from 0 hat and from 1 hat. So when we do this, we reduce the cost a lot, because effectively we do, it's like doing a binary search for the backward coupling time. That results in a cost of the order of t star log t star instead of t star to the square. So monotone CFTP with this doubling strategy can be an actually efficient algorithm to sample from certain distributions, the Ising model being a primary example. But still it applies only to some cases, typically discrete cases. And in fact, an early result by Foss and Tweedy, I believe 98, shows that the constructions of Propp and Wilson apply to chains that are uniformly ergodic. That is, if we want the meeting time to be finite almost surely, effectively we can show that this would imply the uniform ergodicity of the Markov chain xt. And that, of course, is a bit concerning, because many MCMC algorithms do not produce uniformly ergodic Markov chains, especially on continuous state spaces. On discrete state spaces, finite discrete state spaces, this is not restrictive, but it is restrictive on unbounded continuous spaces. So there has been many attempts at relaxing the assumptions of monotone CFTP. For example, the so-called dominated CFTP or bounding chains method, for example, of Kendall, Muller, Huber, and many others. And there has been some successful applications to real MCMC problems. So let's mention a few and also a few names of the contributors. This has been an active research area since the mid-90s and up to the recent years. Perhaps one of the most developed area of application of coupling from the past is sampling procedures for point processors, typically using something called dominated CFTP. And there are various works by Kendall in the UK, Muller in Denmark, Geyer at the University of Minnesota, for example. There has been some application to slice sampling. Slice sampling is quite amenable to a certain partial order when employing common random numbers to perform updates. And so this has been explored in various works, for example, Antonietta Mira, Gareth Roberts, Kerry Mangerson, Christian Robert, or Anne Philip, for example, have early work in the late 90s, early 2000s on some practical applications to slice sampling. There has been also work on other types of algorithms, for example, certain parallel tempering algorithms. This has been explored by Jeff Nichols and Muller again. There has been applications to also certain types of Bernoulli factory problems in recent years. In particular, the very recent PhD thesis of Giulio Morina explores this topic. There are recent applications to sampling colorings of graphs and various problems of combinatorics, applied probability, as well as statistics. So coupling from the past has been a research direction among the most exciting directions in the past decades when it comes to simulation methods in general, and simulation methods based on Markov chains in particular. Unfortunately, for most MCMC settings, for example, most examples in Bayesian statistics, CFTP remains hardly implementable. In many cases, we just don't know how to make any of the existing CFTP methods work. And so there's still a lot of research questions that are open in this area. That's it for today. We've looked at couplings. First, couplings of random variables, then couplings applied to Markov chains to obtain geometric ergodicity results primarily. And then in this last part of the course, we employed couplings in order to obtain concrete convergence diagnostics for MCMC and biased estimators of the expectations of interest with respect to the target. And finally, with coupling from the past, exact draws from the target distribution, all based on couplings of Markov chains. If you'd like to know more about those topics, of course, there are the lecture notes with references in it. I'll be more than happy also to provide more references if you have specific interest, specific questions on those topics. And please don't hesitate to keep in touch and to reach out by email if you'd like to discuss those topics of couplings in Monte Carlo any further. I hope you enjoyed this course. Thank you.